Yes.
A very good evening, Professor Arun Grover, sir.
Namaskar, sir.
Sir, am I audible to you? Professor Grover, sir.
His mic is muted.
Hello, can you listen? Can you hear me?
Yes, sir. We can hear you. Yes.
Dr. Neetu, we still have 5 minutes time because we have given time of
Yes,
6:30. So we will wait for 5 minutes.
sure. नमस्कार जसविंदर सर।
नमस्कार नीतू मैम। नमस्कार। ठीक ठाक हो? मेरी आवाज सुन रहे हो?
हाँ जी सर, बिल्कुल आपकी आवाज बिल्कुल क्लियर है।
ठीक है,
तो सुन
थैंक
रही
यू
हूँ।
थैंक यू।
थैंक यू।
Welcome, Professor Grover. Namaste.
Namaste, yes. Hello.
Thank you for sparing time for us, sir. Thanks. Am I audible, sir?
Yes, yes, I can hear you.
Okay.
नमस्कार सर, आलूले सर, नमस्कार।
Namaste. Namaste.
गुड इवनिंग रेखा मैम।
नमस्कार अरुण ग्रोवर सर। नमस्कार आलू वालिया जी।
नमस्ते जी।
सभी को नमस्कार। हाँ, आलू वालिया सर नमस्कार।
नमस्कार।
नमस्ते जी।
नमस्ते जी।
नमस्ते जी।
नमस्कार
नमस्ते
मैम। मीनाक्षी मैम,
नमस्कार जी।
नमस्कार।
नमस्ते जी। क्या हाल चाल? बढ़िया, खूब बढ़िया चल रहा है नीतू मैडम आपका
थैंक यू
प्रोग्राम।
मैम, थैंक यू। इट्स ऑल द एफर्ट्स ऑफ ऑल
और
मेंबर्स ऑफ
आता है,
302।
बड़ी अच्छा, खूब सीखने को मिला, जो मेन पॉइंट है।
थैंक यू।
Evening, everyone.
वेरी गुड इवनिंग
गुड इवनिंग जी।
वंदना।
Good evening.
रेखा मैम, आर यू एबल टू अनम्यूट योरसेल्फ?
Yes.
ओके ओके, राइट, फाइन।
नमस्ते रेखा मैडम, बहुत दिनों
Namaste.
बाद नजर आए।
Namaste, madam. Was not allowed to go, look at the screen for some days.
ओह अच्छा,
So that is the reason.
तो अब ठीक
But
हो?
I'm back, yes.
ओके ओके, गुड।
Good evening to all of you, ma'am.
Good evening.
गुड इवनिंग।
अ वेरी गुड इवनिंग।
Namaskar. A very warm welcome to the last day of our very renowned program, that is Alice in Quantum Land. Finally, Alice is ready to depart from the quantum land, and we are marking it as a 7th day. But what else can be the blessings of the day or the evening, I can say, when we have the presence of very renowned, famous physicist, Dr. Arun Grover. Professor Arun Grover needs, or Sir, respected Sir, needs no introduction. Being a luminary from TFR, former Vice Chancellor of Punjab University, Chandigarh, numerous publications, patents, records, and many other achievements with the education from the Imperial College London also. Sir, it will be like it's so deem it a privilege to introduce you before all the audience because this is a gathering across nation. We have many scientists, researchers, physicists, persons from IAP, APT, so on, who are looking forward for your valedictory remarks and the concluding session for the last day of our Alice in the Quantum Land. My dear colleagues, students, also Government of India has marked a great emphasis on the research on quantum physics, as Sir will also discuss that a great deal of funding is dedicated to the research on quantum physics. So without taking much time and intervening between the audience and respected Sir, I invite Grover Sir for its valedictory remarks as a chairperson of the valedictory session. Welcome to you, Sir. Thank you so much. Sir, you have to unmute yourself.
Thank you.
Yes.
So good evening all. The speaker for today, Professor Urbasi Sinha, Professor Ahluwalia, the host, and of course, my colleague, Professor Manjeet Kaur, who also gave a talk in this series. So I'm indeed very happy to have an opportunity to become a part of deliberations of this national workshop on quantum physics, which commenced 5 days ago on April 9. So at the outset, I wish to offer apologies to Professor Ahluwalia, the President IAPT, for having missed the announcements of 2 workshops in the domain of quantum physics hosted by the 2 regional chapters, RCO2 and RC19. I am a life member of IAPT and also included in the WhatsApp group of IAPT. However, somehow I missed both the announcements. WhatsApp group sometimes has lots of mails in a day and one sometimes misses important announcements, but however, this is not an excuse for my lapse. So we are on the concluding day, April 14th. April 14th is an important day in India as Ambedkar's birthday. But since the year 2022, it is being commemorated as an annual World Quantum Technology Day. I became aware of it as a member of IUPAC Commission C14 on physics education in the year 2021, but I have actually not participated in the deliberations or commemoration of annual Quantum Day in the last 2 years. So I'm very happy that this year at least I'm making my presence in this community of physicists for this important day. So the purpose of launching annual Quantum Day has been to spread awareness of new applications of quantum physics in the form of quantum technologies. And quantum technologies are anticipated to bring about unforeseen changes, and you have learned about it in the last 4 days. The advent of personal computers 40 years ago and the smartphones 20 years ago had necessitated the spreading of awareness of bit literacy to all, not just to the educated people, but also to those who never had an opportunity to go to a college level at all. Everybody needed to be told about what bit literacy is about, digitalization is all about. So introduction of quantum technology would require spreading the awareness of qubit literacy in addition to the bit literacy. I had myself approached Professor Arvind on behalf of Punjab Engineering College to give a public lecture on qubit literacy on April 22. So this lecture is scheduled in a week from now. From the schedule of your workshop, I gather that Professor Arvind gave a talk on April 9 with the title From Quantum Mechanics to Quantum Technology, a journey of 100 years. I missed that talk, but I'm sure that talk must have been very educative for students, teachers, general publics, and even experts. So, as we just learned in the beginning, that the government of India launched National Quantum Mission precisely on April 23, 2023. So it's less than 1 year ago. And this mission aims to position India amongst the global players in the field of quantum technologies by developing indigenously capabilities in areas such as quantum computing, quantum communications, quantum cryptography, quantum sensing, quantum metrology, and the quantum materials which could be needed for all these things. Quantum mission is special in the sense that no products stand available for use outside the nascent laboratory stage anywhere in the world. So the National Commission, this National Quantum Mission, has been launched much in parallel to such missions launched elsewhere in the Western world. We are not very far behind in trying to chase a new technology. It's my impression that the mature scientific communities in academic institutions in India have the potential to make significant contributions in these domains in the foreseeable future if an appropriate mechanism can be put in place to encourage the teachers, scientists, and the technologists with different expertise to synergize their efforts towards the well-defined verticals. This hope stems from the fact that a large number of higher education and research institutions like IISERs, newer IITs, triple IITs, NITs, newer central universities, and deemed universities, etc., have managed to induct highly talented faculties trained in frontier areas of science and technology from premier institutions within India as well as from those across the world. Our speaker today belongs to that category. The national academic institutions. So it's my belief that in spite of highly talented researchers, an apparent worrying weakness in our present system is that the research groups and departments in our institutions are typically small in size, less than half a dozen faculty members in a given area in any institution, and they remain subcritical in comparison to the competition prevalent at the global level. This difficulty can be overcome if we innovatively and proactively promote interdepartmental, that is, departments in a given institution, and interinstitutional collaborations towards the well-defined targets of national quantum mission. The national academic institutions in India typically attract the best young people from all across the states. If the research facilities of teacher scientists desirous of participating in the goals of quantum mission can be upgraded and well supported with training of human resource, masters, doctoral level students in India, and they are provided recurring consumable and travel expenses for movement within India. That means you have to move to different institutions to interact with PIs who would be located at different institutions. So I hope if an innovative mechanism can be found, then we can skill young people in a continuous manner for research and development in the cutting edge science and technology, and aid the industry in having some production of as and when the products would come. A viable plan can be nucleated on behalf of interinstitutional consortia centered around national institutes of repute in different regions of the country. Each of these consortium can run a hub and spokes model, and by now, quite a satisfactory examples exist in our country. One member institution can be identified for awarding a degree. A few of the institutions can assume responsibility for providing broad-based hands-on training in instrumentation and techniques to the master students and PhD students working with different PIs. Different students, after little bit of coursework for 1 to 2 semesters, can be assigned to work with PIs drawn from the different institutions, and they can be moved around with a sumptuous travel support. So this way, an innovative way of creating schools in different regions of the country for supporting this national mission, in principle, can be evolved. It won't be an easy task, but prima facie, it is feasible. IISc, Indian Institute of Science, Bangalore, launched a program on quantum technologies 2 years ago, and they are running it in partnership with IITs. But one such program is not adequate. We need large number of such programs spread across all parts of the country, in which not only the university teachers, but we should also be able to entice the college teachers to participate in such programs by providing sabbatical leave to the college teacher, paid sabbatical leave to the college teachers, so that every college teacher who has expertise in such areas can become a part of this national mission, okay, once in 6 semesters. And the leave salary of that teacher inducted into that mission be provided by the funding from the National Quantum Mission. This way, we will be able to have a large number of people participate in a national mission. It may sound fancy, but I believe it is possible. And I hope the purpose of running these workshops, where you are making large number of people aware of what all this is about, that will reach a next stage in larger and larger number of people desirous of participating in such a mission are enabled to do so. So these are my remarks or my observation for you, for you to worry about and see how it can be institutionalized, on how the IAPT chapters can exert pressure on the government of India that everybody should be taken along in the pursuit of this national mission. Thank you very much.
Thank you so much, sir. I'm sure that all participants, they have been enlightened with your vision as well as the detailed discussion how quantum physics can be taken further. And definitely it is need of the hour at the moment. And as an Indian, we are committed to do better and we will continue to do so. Thank you so much, sir. If any participant has questions for Grover, sir, then please drop in the chat box. And wherever the time permits, we will ask, sir. And to continue the next day, before I move on to our honorable speaker, Dr. Professor Urbasi Sinha, I would like to acknowledge the presence of all the panelists as well as experts who have been with us for all these 6 days in the journey of our Alice in the Quantum Land. We are honored to have your presence and thanks a lot for sparing your valuable time, be it offline as well as the online. Thank you so much. Now, to move on further, we have our speaker, Professor Urbasi Sinha. She has joined. Ma'am, am I audible to you? Just to check that everything.
Yes, yes, yes,
Yes.
please. Thank you.
Thank you so much, ma'am. Professor Urbasi Sinha heads the Quantum Information and Computing Laboratory at RRI. This is one of the first lab in India to manufacture and establish the use of entangled and heteroid single photon sources towards various applications in quantum science and technologies. Professor Urbasi research areas include experimental secure quantum communications, including quantum key distribution in free space, fiber, and integrated photonics, quantum teleportation, as well as device independent random number generation, high dimensional quantum information processing, including photon quantum computing, fundamental tests in quantum optics and quantum mechanics, including generalized measurement and various studies based on static and dynamic properties of entanglement. One of the key projects being led by the lab is a collaborative project between RRI and Indian Space Research Organization ISRO called Quantum Experiments with Satellite Technology, which is India's first funded project on satellite-based long-distance quantum communications. Such an enlightened CV and really a lot of dedication and work can be seen from all this, and especially your project with ISRO. So we are looking forward for your discussions and views and your presentation. Where I think all are waiting to listen to you, ma'am. So over to you.
Thank you very much, Dr. Sharma, for this very kind introduction. Can you hear me? Can you hear me well? Yes, and of course, thank you, Dr. Neetu Verma, for the kind invite, and of course, Professor Grover for this very enlightening, introduction and to the National Quantum Mission. So it is very interesting because I get to speak on World Quantum Day. So I also will say a little bit about both NQM and World Quantum Day as a part of my talk. I must apologize, I wasn't able to join the forum for the last few days because I have been pretty ill with flu. And so today is my last day of antibiotics, so it is a cause to celebrate. And I think I will manage to pull through with coughing just 2 or 3 times. So I have been just increasing the frequency over the last few days. So sorry, Dr. Verma, I couldn't attend the 9th one. You had invited very kindly, but then I would have just been smiling.
No
So
issues.
that's a worst day. So thank you. So I will share my screen, and I hope somebody will verify that it is visible. Can you kindly confirm that you can
Yes,
see my
it's
screen?
visible,
Yes,
ma'am.
we can
It's
see.
visible.
Great.
We can
Yeah.
see it perfectly.
Now also let me change the speaker view. Yeah, great. Also, once in a while, please do tell me that you can sort of hear me, because I have given one talk since 2020 where I actually have spoken for half an hour without an audience because they lost the internet connection. And so since then, every 10 minutes, I take a break and ask, am I still audible? So kindly bear with me on that. So thank you very much for this kind, invitation. I have been participating in various IAPT events. Somehow or the other, I have been doing this for the last few years, and also given the talk on, the Nobel Prize in 2022. And so I have been very, fortunate in being associated with several events organized by IAPT. And so today's is, of course, very special because it is a national workshop on quantum, and then today is the final day, and of course happens to be World Quantum Day. So my talk is on the magical world of photons, because, and of course, that is what I work with. And so the way it is, organized, I'll speak a little bit about quantum and some of its features just to remind you. I know we have had some very nice talks, seen the schedule over the last few days, but just, it always helps to have a little reminder of one or two, sort of key elements, and then move on to photons. So just one second. Yeah, so this is essentially how our journey began. This was December 2012. And so I joined RRI in March 2012. And so our lab was inaugurated in December. And we have been very fortunate in having very, well-known quantum physicists from all over the world attend this inauguration. Here you can see, can you let me just change this to a pointer, which is a bit better. Yeah, so can you see this particular gentleman here in the shots right next to me? This is actually, you may have heard of the BB84 protocol, which is a very famous quantum communication protocol. So this is Bennett and Brassard, and so this is Gilles Brassard, actually. So we were very fortunate to have him as one of the people inaugurating the lab. And since then, we have, continued our journey in quantum communications and beyond. Well, the first few minutes is going to be about quantum mechanics, and this is, of course, always a favorite quote. And, it always never hurts to actually have this very handsome physicist's picture on the slide. We always need just an excuse to show Richard Feynman. And so he, of course, very famously said that he thinks he can safely say that nobody understands quantum mechanics, and this was 1965. And of course, we've come a long way since then. But then we can still, add a little maybe asterisk, a little bit of symbol here and say, nobody completely understands. And that is actually the beauty of quantum, right? The fact that there is always some mystery associated with things is what gives it this enormous power and potential, and we now have a national mission on its applications. It is not, it is just didn't happen just like that. It is because of all this beauty that is hidden in its principles, which still remains beautiful and will continue remaining so. And so this is what is amazing and keeps us going. Having said that, the impact of quantum in daily life is not new. While we heard, Professor Grover talk about the national mission, which has been launched in April 2023, and now, we are going through the proposals and so on. This is, the excitement of quantum, however, is not new. And so all these things that we see on our screen here, as you can see, these are all examples of objects, of applications which use quantum science. Now, this, for instance, is a laser, right? And so most of us here, may have had some kind of correction done to the eye. I mean, of course, you can wear glasses, but you can also get a laser eye surgery. So now, when the laser was invented long time ago, nobody really realized that, it'll be used for something like, for instance, this is a laser pointer. I mean, so point is that, now it has become very commonplace. So there are many applications of quantum which surround us. Sometimes we may forget that they actually are, in fact, applications of quantum. And so these are all examples of things which we come across sometimes every day, sometimes maybe, hopefully not every day, this MRI machine, hopefully not every day, but we're all familiar with it. But these are all based on laws of quantum mechanics. So this particular point is very important, and I'm sure Arvind gave a very nice talk on the history over the last 100 years. So if it's 100 years, that means it's not a new topic, right? And because it's not a new topic, even its applications are not new. And so these are all examples of applications which are already there, and we are living with them, right? So this is one important thing. And so this is what is called the first quantum revolution, right? And having that, quantum mechanics is one of those things which is also very rich in terms of its legacy, right? And so all these, examples that you see here, let me just try to get this thing off the screen. Yeah, so these things that you see, these are all examples of contributions in quantum, which I guess Arvind may have gone through if he went through the 100 years history. But these are all people who have made seminal contributions to quantum, and of course have been awarded the Nobel Prize in Physics as well. So it may be right in saying that, quantum and its applications perhaps have probably a very large share of the Nobel Prizes in physics so far, if not the largest, right? So these are all examples of various contributions which are all Nobel Prize winning, right? And it continues. So these are all, pictures of very famous people, stalwarts in our field of quantum, right? Even the Nobel Prize in Physics 2022 was for quantum, and this was awarded to Alana Spey, John Clauser, and Anton Zeilinger. Having said that, this is particularly special for me and for, our lab and everyone who works with photons, because, this was given for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. And so this is some of the community feels that this is a bit of a delayed Nobel Prize. This should have happened much earlier, but we are all very pleased that it finally did happen, because this is a beautiful prize, and I'm sure many of you would resonate with this thought that, this prize is given to these three people for work they have done over decades. So, John Clauser started, this was the first experiment. Alana Spey did experiments over a couple of decades, improving on various things, eliminating loopholes, as they're called. Finally, Anton Zeilinger, of course, also did many things over those decades and did the loophole-free Bell, right? And so this is something which, is going to be very nice if we remember, even let's say in the National Quantum Mission, because while we have a focus on technology of, of something which will come out as a product and so on, we have to remember that something which will have a long-term impact need not happen in a day, right? And so this Nobel Prize is an ode to how science is ideally supposed to be, right? That, you keep on doing things, keep on improving, and finally something comes out which is beautiful. And it takes time, it takes patience, it takes resources. Right? And so this was a beautiful prize because it was not only for the, the discoveries, but also for the the technology, which is quantum information science. And if you're interested in this, please do have a look at this article I was invited to write, in which I've gone into great details about the physics behind the Nobel Prize. It would be nice if people did not start drawing on the screen, because it's just a little bit not very polite, because I don't have any control on the red line which has appeared. However, having said that, I would ignore it and say it is a beautiful prize. Okay, so having said that, few concepts in quantum, and I will appeal to Dr. Verma, Dr. Neetu Verma. You can hear me. But so I will take this pause every.
Yes, ma'am.
Yes, thank you. And of course, I can see people are drawing on my screen, so I'm definitely online. But
I'll check it.
yeah, great. So, having said that, a couple of concepts I like to touch upon, and I know that we have a varied audience. So some may be from the quantum, but some may not be. So just to ensure that you are all on the same page regarding a couple of things which we should take home. One of them is of course quantum superposition, which is perhaps one of the most talked about principles of quantum mechanics, and it is a very interesting thing. So if you think about a light switch, you usually think about it being either off or on, right? But then in the quantum domain, if it's a quantum light switch, it could be a little bit on and a little bit off at the same time. Okay, and so this sounds a little bit spooky, but that is how quantum sounds. But it is true that you can actually have access to a large class of states. In fact, it can be an infinite number of these possibilities of a little bit of this and a little bit of that, following certain principles. So that is what is a superposition, where you have not just one or the other, but a combination. And that is what qubit is, right? It's a superposition of, let's say, the 0 and the 1, which could be defined in different systems in different ways. And excuse me. And so this is what gives you the power of quantum computing, because it's because of superposition that you have access to this large Hilbert space, and then the quantum algorithms work in a way that make certain applications, certain algorithms way faster than what would happen in the classical computing parallel. So this is superposition. Going on to entanglement, again, that is an even harder concept. And if I don't want to get into the math of it, then let me just remind ourselves. I know I have audience here, some of who are above, the 40 age group, let's say, and so you would know this era of Bollywood films that some of us were children and some of you were a little older, some of you may not have been born. So this was the era in which we had this theme going on in Bollywood, where you would have these brothers, these twins who were separated from each other at birth, more famously in Kumbh Mela, right, which is one of our very popular annual religious events, right? So they got separated, and traditionally one of them would grow up to be a police officer, and the other one would obviously grow up to be someone against the law, let's say a gangster or something like that. And so then ultimately they would end up, of course, meeting. And in some of these movies, they would, of course, have a face-off, and with the common factor being their mother. This was a theme which we have seen in many movies. Why am I bringing this theme? This theme is interesting because this actually is what is the basis for quantum entanglement. So these two particles, which have been produced at the same time, at birth, they share a certain correlation, which they continue sharing in spite of having grown up in different circumstances, in this case, the brothers. But then for the particles, they could be thousands of kilometers apart from each other, but they still have that correlation. And it is using this correlation, this quantum correlation, which does not have a classical counterpart, that I can actually, explain, and it forms the basis for secure quantum communications, for instance. So quantum entanglement is one of those features without which we won't have many of the applications that we are so happy about. Okay, so these two topics I actually like to just talk about before I go on to my stuff about photons, okay? Because of course I will be dealing with superposition and entanglement, as you will see. So having said that, quantum, so what have I done in the last 10, 12 minutes is I've told you that, quantum has been around. Of course, it has a 100-year legacy, and it has already done a lot. We have all these applications which are around us. Then why are we so excited today, right? Of course, that must be a question that should come to us. Is there anything, what is the renewed excitement that we're talking about? Because now we can do so much more, dream so much bigger. And so this is the idea that what is it that now we can do, which we could not do, let's say, few decades earlier. And so these possibilities of, new applications that we are looking at over the last few decades as globally, right? This is what is a renewed excitement in quantum. And that has happened because now our precision has increased a lot in dealing with the single quantum state, whether it's a single photon, a single atom, single ion. We are able to access it, we're able to manipulate it, we are able to measure it, and all these possibilities did not exist some time ago. And with that, we can have this huge potential in computing, security, sensing, etc., etc. That is the new excitement that makes us, excited all over again. So with that, I go on to a gender-specific slide, right? So having said that, although I can't really see my audience this time around, but I'm sure my audience consists of both male and female members of society, all genders, right? And so I would say that this left side is something that at least some of us, at least the ones who belong to my gender, would accuse the other gender of being more comfortable doing, right? So this left side scenario is something that some of us are very, very, used to seeing. And I do really believe that there is a bit of a gender bias here, that and reverse gender bias, that let's say the other gender just likes and is better at doing this, right? And then there is one scenario on the right that you can see, which, as you can see, is just the opposite of this, right? So here everything is nicely separated out and ironed out and even put in cupboards and all that. So I would say again there is a gender bias. The right side is also something maybe some of us are better at, or some of us are forced to be better at. Depends really on our mindset. But then this definitely is a contrast. One thing, however, is there is a commonality in this contrast. What is this? This is an example of an everyday problem that is not equally hard both ways. As you can see, from left to right, it will take me a long time to go. Yeah, because separating out, this is a time-consuming process. But if I want to go from right to left, all I need to do is just pull things out and drop them on the floor. Right? This is a much easier process. But they are reverse of each other, but they're not equally hard both ways. So this is an example, which is, of course, it's done with a sense of humor. But then having said that, this is the basis for our current security. What does that mean? It means that, what we are basing our current security on is this class of problems, which is one way hard. For instance, factorization. So if I tell you, what is 3 times 7, I'm sure people are already thinking 21 in their minds, and even if it's an online audience. And if I tell you, what are the prime factors of 114371, you just can't spout out the number like that. So factorization and multiplication are opposite of each other, but not in their hardness. And in fact, what I mean by hardness is the amount of time it is taking, right? So this is what, for instance, the RSA protocol is based on, which is essentially one of the most popular protocols for keeping our data secure. Having said that, conventional resources, they grow very fast. And today's hard problem could be solved tomorrow using brute force attack. It could be classical or quantum, right? So my security should be independent of future advancements in computational power, new algorithms, or new technology. And this new algorithms could be classical or quantum. So it should be future secure. It cannot be based just on this, one-way hard problems, because those could be cracked. And so that is what brings in the first great, application of quantum, new modern quantum technology, which is quantum communications. Okay, quantum communications is a paradigm change in security, which is based on laws of nature, okay, and not on mathematical hardness of problems. And I'll give you some more detail on quantum communications as I go on when I talk about the photons and what we do with them. And so this is a whole shift in how we are dealing with security and using laws of nature, laws of quantum physics, and not mathematical hardness. This is one very exciting modern quantum technology. Excuse me. Going on to this scenario, and please bear with me, this is not something I have drawn. This is an illustration by a very, obviously talented artist. But what is this illustration of, right? it's I mean, what does this bring to your mind? You know, it is a scenario where I can see that there's a little girl, who's not very happy. She's quite sad. She's sitting in a world where, all these fish are dead in the oceans, right? There's hardly any leaf on any tree, or hardly any tree even. Yeah. So what is this depicting? This is depicting a scenario of extreme climate change, right? And so, having said that, this is a possible future world, right? If we don't take action now, this is possible because, the indiscriminate way in which we have done industrialization, while of course that has given us a lot of, good things, many things have been done in a thoughtless manner, right? And if we don't take action now, then all this carbon in the atmosphere, all the pollution in the ocean, it could definitely reach a scenario where we are looking at this as a reality. Here we have another interesting. So this is an example which is not often taken. So I sort of choose to discuss it this way because when we talk about quantum computing, we talk about a machine which does computing way faster, and then not much else is said that okay, I can do something very fast. But then what is it? What can a useful thing which I can do very fast? For instance, is I can simulate chemicals. I can simulate new materials. And this is already happening now, right? Simulate new materials which maybe can absorb the carbon from the atmosphere going down the line. So this is an example of a very social, application of quantum computing, socially relevant. And of course, if we use it properly, we could avoid this catastrophe. So going on to the third application, which is taking a lot of interest now, it is, an example I have taken, which is this is the Indian map, as you can see, and these are all, areas in India where we have oil wells. Okay, so what is it that we would be interested in as an oil and natural gas industry? Maybe detect new oil reserves, maybe detect and locate gas leaks, right? And so these are, of course, things which are being done. But imagine a scenario where you can do this way more precisely than what is being done now. Detect new reserves which otherwise are impossible using classical means. That is quantum sensing. For instance, this is a turnkey, transportable, and easy to operate quantum sensor. It's already available, okay? And using this, you can sort of put this, on a scenario, volcanic region without going there yourself, and you can use this for volcanology. So, a machine which is just stationed there, which gives you all this activity. So these are all examples of possibilities. And of course, I've just taken a few examples just to excite your imagination. There are plenty more, right? Of quantum technologies, modern quantum technologies. So having said that, we already heard about the National Quantum Mission. So what are we going to do in India towards this? Right. So the National Quantum Mission was launched in April 2023, and we are going to, develop all these technologies that I just talked about, whether it is magnetometry, whether it's new quantum materials, different sources, detectors, quantum computers with different capabilities. In quantum communications, we will have long distance quantum communications using satellite based approaches, the kind of project that we are already working on and, for a long time now, as was mentioned earlier in the introduction. Then long distance communications with other countries, fiber based quantum key distribution, and of course, a new form of quantum communication, which involves what are called quantum memories. Again, something our lab has been working on for several years. And so we'll have 4 thematic hubs on these various topics. Okay. And idea is to seed, nurture, and scale up scientific and industrial R&D, vibrant and innovative ecosystem in quantum technology, and hopefully make India a leading nation in the development of quantum technology and applications. And what Professor Grover said in the beginning is, of course, fantastic, because the whole mission would be successful if we can involve more and more like-minded people from different walks of life in it, right? It need not only be a physicist, right? So the quantum technology is something where different people can contribute in different ways, whether it's physics, whether it's engineers, mathematics, computer scientists, even astrophysicists. This is in the scientific domain, but you can also be a user. So you can also help in developing use cases for quantum. So there are many things to be done, and I'm sure there is place each and everyone who is motivated to contribute towards it, not just wants to contribute because this is, something which is giving me some resources. Then that is not it. You have to have a good idea, which actually is well motivated. And then, of course, I'm sure there are lots of pathways towards contributing. Okay. So having said that, coming to photons, which is of course what we contribute with currently. Photons, they remind, and as you may, some of you have heard me talk before and also know me personally. So you know that, I just cannot keep talking without having a little fun once in a while, right? And so this is, something that I found on the internet, which is a very nice cartoon. So it says, along with antimatter and dark matter, we've recently discovered the existence of doesn't matter, which appears to have no effect on the universe whatsoever. And this is of course said with a sense of humor, but then in some sense, it's something that people may think about photons, right? If you know about photons, they don't have mass, they don't have charge, right? So they don't have matter, obviously. And so you may think that they don't matter ultimately, but that's not true. Photons are very, very, critical in all these technologies that I talked about. In some of them, they are quintessential. And so photonic quantum science and technologies is one of the most important areas in quantum. Okay. And so with that, I will take a pause and ask Dr. Verma again that I'm audible, visible, and
Yes, sure, perfect.
Yes,
great.
Sinha,
Thank you.
you're
Yeah.
audible.
Great. Yeah. So I will move on to my photons now. Okay. And so, and of course, I know that I can see there are 100 odd people here. So some of them obviously are students. And so if you want to know more about photons, do have a look at these resources. So this one is a very high level review. So it is not very technical. This one is a book chapter. Okay. And so if you are interested, have a look at this. And of course, this one, if you have the hard copy, great. But otherwise, if you get into a paywall, you can email me. Maybe I can send you a soft copy. It's not the most, so, I can do that as an author, right? So this is, this tells you a bit more detail about photon sources and their applications in quantum science and technologies. Having said that, as was already mentioned, we are the first lab in India dedicated to photonic quantum science and technologies. And so we are working on all these areas. Excuse me. Quantum information processing, quantum fundamentals, quantum computing, quantum communications, and quantum sensing. Okay, and this is more in detail. Before going to detail, this is our mantra. Of course, for people who know, the legacy is not what we are trying to motivate here. The legacy is not great, but then the quote is very nice that, today's science is tomorrow's technology. And so our lab is a very healthy balance between pursuing fundamental aspects of quantum science and understanding it better, as well as applying it to all the technologies that we have been already talking about for the last few minutes. So we are doing a balance between both, and we do believe as physicists and scientists, we should be, encouraged to do this all, because we cannot just become product developers. For that, we have the industry, right? And so we focus on both the science and the lower TRL technologies, and then the industries can take up for the higher TRL programs, right? So a little more in detail in quantum communications, we have several projects in quantum key distribution, teleportation relay repeater, random number generation, integrated photonics. In quantum computing, we have our own photonic platform. I'm also in the advisory board of the JESDA Open Quantum Institute. This is a beautiful initiative which is now at CERN. And so this is you're working towards, it is a global enterprise where people are working towards making quantum technologies applicable and useful for the sustainable development goals of the United Nations. And so I am also looking at some use cases myself, but I'm also there in their core advisory board. And RRI Bangalore is a spearheading partner as well for the OQI. In quantum sensing, we're using working quantum imaging using entangled photons, as well as a new type of measurements, which gives us a very high precision compared to the usual ones. And then we also work on precision tests of fundamentals and foundations of quantum mechanics, as well as quantum gravity. Okay. This is a snapshot of our lab, so please do come and visit us if you wish to actually learn more on site, right? These are some of the current people. And of course, as I always say that, the lab is just a bunch of optics and optomechanics. It's the people who make the physics and the science happen. And so this is the current lot who are mostly seeming happy in their pictures. And of course, we've had several people who are now in different locations doing very well for themselves. So I'm very proud of our past, present members of the lab. We also have a lot of collaboration. A lot of the work we do is in collaboration because, we do believe that doing something in silos is not the mantra right now. We want to be globally relevant, and for that, we need to ensure that we are doing things which are in sync with what is happening in different parts of the world, right? And so these are some of our collaborations with outside India, initiatives. And then, of course, we also have lots of collaborations within India. So, bird's eye view of our science. So, for that, this is a video where you can see how photons are created. And of course, it's a little bit difficult to show you the lab on a slide, but this is sort of the principle. So you have a very strong laser which is incident on a crystal which has a very high chi2 nonlinearity, and that gives rise to, among other things, a pair of photons. Okay, and this pair of photons actually goes on to form a cone. Okay, and so just 1 second, I will just try to go to this non-laser pointer one, because then I can stop this. And so this cone, I won't get into the details of why cone, how cone. This is, of course, a lot of math goes into that, but this is, of course, a pictorial view. But having said that, now we go on to an actual picture from the lab. So this is an actual picture of photons. Okay, so if one photon is here, the other one will be here. So they come in pairs. Okay, and this particular point that you see on the screen, this intersection point. Now, this is a very special point because this point you don't know which cone it is coming from. So if one of them comes from the right, the second will come from the left. But here you can't distinguish between them. And so this intersection point is what is called the entangled state. Okay? So if I want to deal with entangled photons, then I need to harness it from that, intersection point. Okay, and so this is a picture of an entangled source from the lab, and you can see, a little bit of a close-up, and there are different ways in which you can have these entangled photons. And this, of course, is something which is taken on a very highly sensitive camera. And so this is just a little bit of a lab, just a close-up of one experimental setup, just, to show that, there's a lot of optics and optomechanics involved, and there's a lot of fine alignment involved in these processes. Okay, so this is the strong blue laser that you can see. Here you can see this square thing. This is the crystal. Okay, and so this has this very high nonlinearity. And so after that, you actually give rise to this pair of photons, but you never see photons. And of course, you can't see photons by naked eye, but then you know that they exist. So they are a pair. So, then they hit upon what is called a beam splitter. This guy over here, this one. This is a beam splitter. So one of the photons goes straight and the other one goes to the right. Okay, and so how do you know that they actually exist? You measure them simultaneously. So if one of them is hitting the detector on the left, the other one is hitting it on the right. And so if they are actually photons from the same pair, then they actually give rise to what is called a coincidence peak. And this is a live coincidence peak that you just saw being measured in the lab. So this is a way in which you can, characterize a photon source. Okay, so this is just to give you an example of how things work. And I'll go back to my pointer. And so these are some of the pictures. Okay, and so these are some of our recent results. I'll skip details of them, but just pick up one of them because, it is something which we are very proud of and again has a little bit of a correlation with what I already talked about, which is the Nobel Prize in Physics 2022. As I said, it was given to these gentlemen for their experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. So in this violation of Bell inequalities, this is something you will hear, and of course, in today's lecture, I cannot really get into the details of what they are and so on and so forth, but it just suffices to say that violation of Bell inequalities actually disproves what is called local realism. Okay, and in other words, quantum mechanics is a theory which does violate local realism. Okay, and so by performing this sort of a violation, you're actually giving a proof of entanglement, non-locality as well. So two photons which are not in the same location, which are far apart from each other, and they violate this inequality. Okay. And so this is a very simple description of what happens in this. But what Anton Zeilinger did, and his group, of course, is, and Alan Aspect, So over several decades, what these two people did is they closed what are called loopholes which existed in the earlier experiments. So one experiment after another, they closed one loophole after another. So what is a loophole? Okay. So, so this loophole-free test is what got the Nobel Prize. And so this is something, this paper, this not paper, but this article is something that I would really encourage at least the students to read, because it is beautiful. I haven't written it. So it's a beautifully written piece which tells you about why this is such a great achievement, this loophole-free Bell test. And of course, a loophole-free test tells you that particles can be entangled, that not only that particles can be entangled, but also it is, that a particular source of entangled particles is working as intended and hasn't been tampered with. So what is a loophole? So just to give you an example, this is a very legal term, right? So suppose you and I, suppose Professor Grover and I are actually fighting a case in a court of law. And I am on one side and he's on the other side. So he makes an argument, and what is my job as the lawyer is to find a fault in his argument, which is actually a loophole. So if I find a loophole in his argument, then I am kind of on an upper hand. Then he has to find a loophole in my argument, and so on and so forth. Now, ultimately, the person who will win, or the side which will win, will be the one which has a loophole-free argument. Right? So unless and until you are loophole free, your opponent is going to keep finding that loophole. So loophole free argument is what wins the case. Similarly, a loophole free Bell test is what gives you this complete confidence that you can now use the system for perfectly secure communication and unhackable source of truly random. So a loophole free test is important because it is important because it tells you that quantum mechanics is satisfying it, and it has its importance from a fundamental point of view, but it also has an importance from a technological point of view. And this is that is why it is very special that our lab in 2022 January published this paper on a loophole-free test of macro realism using heralded single photons. So now, what is this experiment? And so this was the first ever loophole-free test of what is called the Leggett-Garg inequality. So this is Sir Anthony Leggett, who also won a Nobel Prize in Physics in 2003, and his then postdoc, but of course now very senior faculty, Professor Anupam Garg. So the Leggett-Garg inequality is what is called the time equivalent of the Bell inequality. Bell inequality talks about non-locality, talks about two or more systems which are separated in space. But what about a single particle? A single particle cannot be separated in space. So a single particle, however, can be separated in time. So it can move forward in time, and you can measure correlations in time. That is the time equivalent. It is, basically as important as the Bell inequality in the time domain. And so over several decades, people have, again, tried to perform a loophole-free test of the Leggett-Garg inequality. And we are very, very, happy and, really, this was a very satisfactory thing that our lab was the first one to perform a loophole-free test of the Leggett-Garg inequality in early 2022. And this, again, sets the basis for using this for all these beautiful applications, which we are already doing. We have several works following this where we have used it for quantum communications in a very new way, which others have not yet done. So this is an example of something which we have done with photons, which is both fundamentally important, but also in the application domain. Okay, and so this is us with Sir Anthony Leggett. And, when we celebrated his 80th birthday at RRI a few years ago. Okay, and so this is a very nice moment for all of us. And also much appreciated. For instance, new scientists actually called us the most watertight experiment of all time. So going on to another application which we do, which is quantum key distribution, which we touched upon a little bit earlier. So this is, of course, the most, I would say, quote unquote, practical quantum technology, because this is already something which there are certain versions of it already in product form, whereas there's a lot of research also that one has to do to make things better, sharper, and tighter, right? So why you should worry? Well, of course you should worry because, I mean, we already started with that. Said this in the beginning of the talk that, these are all examples of applications that that most of us are doing, buying something online, credit card, elections coming up, right? So these are all examples of strategic communication. And so currently this is being kept secure using classical cryptography. But as I discussed earlier, this is based on mathematical hardness of problems, and it will be compromised with, for instance, quantum computers. So we now need to take steps now so that we can prevent this catastrophe. And the solution is, of course, quantum cryptography, right? And so these are, of course, means of communication that we are used to, which are not really secure. We don't need them to be secure, If you want security, then you, of course, take the message, encrypt it in a key, then this is sent to this receiver, who also has a copy of the key in some form, and then you're able to have a secure key distribution and communication between the two parties. So the key distribution is the crucial thing here, right? And this has to be done securely, and this is what is done. This is example of cryptography, and this is something which has been done for ages. Some example, Second World War, the Enigma machine. These are all examples of cryptography and so on. But as I mentioned, what is wrong is that unconditional security is not possible because, we are basing this on mathematical complexity of things. For instance, factoring large numbers. And this is Peter Shor, who has come up with an algorithm already, which can break this on a quantum computer. So already we have a break to our security if a quantum computer becomes, large enough, which will happen very soon. Otherwise, as I mentioned, that is not just that. Computational resources grow very fast. Today's hard problem could be solved tomorrow using brute force attack, classical computing, quantum computing. So we need to be future secure, and that is why we are using laws of physics or laws of quantum mechanics to do that. And these are the various laws, and of course I won't get into the details of how and when, but then these are all examples of laws of quantum mechanics, which is uncertainty principle, no cloning theorem, entanglement. These are all used for our security. Okay. And I skip details here, but this is an example of a slide which sort of tells you that, this is sort of the status, even a few years ago, actually. So these are all examples of things which exist in the market and standardization work going on, a lot of work going on in quantum crypto. And this was the potential for the market. It was a dedicated study that was done. This was even, some years ago. This would have even improved by now. However, so coming on to the last part, of the talk, what is the challenge in quantum communication? So, of course, we know how to do quantum key distribution. We are, we have several protocols. We have several, demonstrations. But it's only useful and interesting if you can do this over a long distance, right? So, me and my student talking to each other in the lab is not perhaps the idea of quantum communication. So if our prime minister, wants to say something securely to the prime minister of some other country, then, that is a long distance. So there is a problem with that in quantum. And so this is very interesting because, we do long distance communications all the time, but those methods will not work in quantum. So if you want to do free space communications, okay, typical distance is, let's say, 100, 200 kilometers, because beyond that, you won't have line of sight because, the earth is round. So you won't keep seeing the other party because, beyond a certain distance, the Earth's horizon will come into play. Then you will say that, okay, why not use fibers? Because that is what, of course, is most commonly done. But the problem with fibers is that they have attenuation. So after a little distance, the signal drops, as we like to say. But what we do classically is we put in what are called classical repeaters. So we have these devices which sort of amp up the signal every now and then, so that the communication continues. But quantum does not allow that because of no cloning theorem. So you cannot have these solutions. Okay, so you need out of the box thinking. And for instance, these are the three methodologies which is being followed globally, whether it is, using quantum memories towards quantum repeaters, trusted repeater-based network, QKD networks, and then satellite-based quantum. So these are all ways in which you can increase the distance without having to do the usual stuff that we do in classical. Okay. And so if you're interested in these things, again, in a popular way, this was an article which I was invited to write just after the launch of the national mission. So, and this one also, again, I can share if you're interested. Having said that, at RRI, we're working on several aspects of quantum communications. We have India's first project on satellite-based QKD, integrated photonics-based QKD, quantum teleportation relays and repeater technologies, as well as new forms of random number generation. Okay, so just to give you an example of the project, which of course was also mentioned in the introduction, this is our project with ISRO. This is called Quantum Experiments with Satellite Technology, or QuIC. It started, now some time ago, right? And so we have been doing several ground-based milestones over the last few years, and a lot of dedication in a bottom-up approach. And our idea is to, of course, establish information theoretically secure quantum communication over large distances and perform QKD between two Indian ground stations using an Indian satellite as a trusted node. Okay. Why is this experiment exceptional? Well, one philosophical point here, it is actually India's first project, as I mentioned, and it started at a time when the field was not that popular. So in fact, it took us a lot of effort to actually get the funding to start this project because people didn't really appreciate the need for such a scenario at that time. Okay. And so we do believe that it was great that we could actually start with ISRO support. And because we do believe that whatever little we have achieved have played a role in putting us on a global map for quantum communications research. Okay. And so this is another project that you will hear a lot about, which is the Chinese satellite project with Mischius, where they have shown several, interesting milestones. But having said that, in their project, what they have is that they have this entangled source of photons in their satellite. Okay. And so they send one photon to one ground station, the other to a different ground station, and then they link up these two ground stations and do QKD. So this is limited in its scope because, at some point, your main quantum source has flown away. So you can't really improve upon it with time because you can't just pull down a satellite, do something and pull it back again. Also, because of solid angle, you can't go beyond a certain distance on Earth as well. So our project aims at demonstrating uplink-based QKD, and this has never been shown before globally. Okay, and so uplink allows for photon source to be at the ground-based lab. It allows for more flexibility with, changing the source even after the satellite has been launched. Okay. And it can include quantum memory elements, for instance, also after the satellite launch. So it gives us a lot of scope for novel, first in the world science. And of course, it is also a very challenging thing to do because it has not been done. So there are many science and technology challenges which we need to solve, which we have been doing systematically over the last several years. Okay. So these are the various, things which one needs to do towards satellite-based QKD. And because, we have a very varied audience, I won't go through the details, but suffices to say that you need to achieve all these milestones, finally ending with demonstrating satellite-based QKD. And in our quest for the same, we have already achieved all the ground-based milestones, okay? So we've done several protocols in lab, between buildings, using atmosphere, between a stationary source, moving platform, identified ground stations, and a lot of analysis for figuring out where to put them, atmospheric analysis, telescope analysis. So all this is already done. Currently, we are in the orange stage, where we are in the process of establishing these suitable ground stations and developing a lab model for our payload. Payload is something which is, the thing that actually flies in a satellite. So that's what we're developing now. And then this will be followed by a qualifying model and then a flight compatible model for the payload. Okay, and identifying suitable satellite requirements, manufacturing the satellite, launching the payload in the satellite, and demonstrating satellite-based QKD. Okay, so I see that I keep seeing people who appear on screen. If somebody could let them in. Yeah, okay. So this is our situation, green, orange, red. And so just a little detail. So this is our first, QKD experiment in lab. And this is in fact India's first reported end-to-end free space QKD experiment, which is published in an internationally peer-reviewed journal. And we are very pleased because it had a key rate and a QBER. These are, the technical things which one needs to achieve in a quantum key distribution experiment. And these were better than the previous one, which was a record held by NASA before us. Okay. And then we have done the first demonstration of QKD between two buildings using an atmospheric free space channel, because if you have to do satellite, you can't remain within the lab. So we have to deal with the atmosphere. Again, we did this way back in February 2021. Then we went on to do in March 2023, the first demonstration of QKD between a stationary source and a moving platform. And this is very crucial because satellite moves. When a satellite moves, you can't keep communicating with it. So you have to keep pointing to it, tracking it and acquiring data. And that takes a lot of effort to come up with the precision that is required to even do quantum communication with such a moving object. And so this is us with our moving vehicle, which was completely developed at RRI. We also did a lot of software development. It is, in fact, we have, RRI's first patent on quantum as well. And so this software is for, QKD, which has within it, the device and process imperfections that are very much essential and part and parcel of the system. So most of the software that you will see available, they're perfect. So the answers that they give are also perfect and they don't match the experiments. So our software, on the other hand, matches with experiments. So it will give you a nice validator tool And also it will give you a, something to do before setting up the experiment, because setting up an experiment is expensive. And we will make this open source once, we have the patenting process of various versions done. We have also come up with different methods of, dealing with atmosphere, of dealing with scrambling of polarization, so various things. As I said, uplink QKD has not been done. So we've solved physics and technology challenges systematically over the last several years, as well as, figured out atmospheric analysis as to where to put these ground stations. Okay. So this is, again, the second and last video of my slide. So you can see free space QKD. So this is my entangled source you saw. And so one of them is going to be sent out. So this is the Alice station. And this Alice station is within our lab, okay, which is where the sender is. And then the other photon goes through this hole in the window across the campus to another lab, which is also our lab, where we have, and so this is my student. And so here we have the Bob station, where we have different kinds of optics and optomechanics to be able to measure the Bob photon. So Alice and Bob being our quintessential sender and receiver. And so this is essentially, free space atmospheric QKD. Okay. Having said that, the last 3 or 4 minutes, I will just digress from quantum communications to tell you that we do many more things, but I just wanted to highlight one aspect because then it leaves you with food for thought. So this is our slide on photonic quantum computing at RRI Bengaluru. So these are all various results which we have from the beautiful architecture that we have created completely in-house of bipartite QDICT based systems, which have their own beauty and challenges. And we're looking at expanding this massively going forward under NQM and beyond. Okay, so this is our photonic quantum computing. Similarly, we also work a lot on commercially available quantum computers. And in fact, the question that we have been trying to answer for a long time is how quantum are these computers? Because, these quantum computers, they have a lot of noise, they have a lot of decoherence. So in spite of that, are they useful? And of course, read our papers to figure out how useful they are. Okay. And this is all fundamental tests of quantum mechanics, quantum optics, which of course forms the basis for all these applications that I was talking about. And especially this one is one of my favorite papers, where we have challenged the second chapter of a quantum optics textbook and said that this Hongmo-Mandel effect, which I'm sure some of you know as a quintessential quantum optics effect, is not quite quantum. We have been able to show this effect using classical pulses. Okay, so we can discuss more if you're interested. So we love challenging textbooks. We love, working on topics which are not always, safe. After all, we need to be quantum safe. And so we work on quantum safety, but we also work on certain topics which excite our neurons and come up with very interesting answers at the end of the day from these explorations. For instance, we are working on sudden death of entanglement. Now, entanglement is something which, interacts with the environment and drops to zero sometimes at a finite time. And then what do you do with it? You, of course, cannot use it for your computer or communication or whatever. So we have come up with a protocol where you can prevent this from happening. And so this is the experiment. This is my student who has now finished the experiment finally. And also this source is special because it is indeed India's first entangled photon source. And it's working very well. And this is a new quantum state estimation method that we found. Again, something very different from the ones that we hear about. This is, as I said, a new quantum sensing tool by using a certain class of measurements called weak measurements, we can amplify certain signals which otherwise would not be, measured because of poor signal to noise. And we have done some very interesting work using this. Okay. And finally, we are also working on quantum information and quantum gravity. And so these are all, examples of experimental proposals based on our underlying quantum information ideas that we have developed in collaboration with people who have been working on this domain of coming up with tabletop experiments for quantum gravity. Okay. So to end, I just want to always acknowledge the fact that, our work has been much appreciated by various sectors of society. And that is something which is very humbling for us, because it just gives, especially the young people, a lot of motivation to, continue with the fervor that they show in their work. And so this is an example of this is a, popular level, I would say, appreciation. This is industry appreciation. This is, very popular, very important forum, Nature India. And finally, this is the government of India, which called us one of their 20 major success stories, which is always special, getting some appreciation from the funding agency. And Similarly, our free space work also received a lot of, appreciation from various quarters. Likewise, our moving receiver demonstration as well. And likewise in quantum computing, and our work has been appreciated again, Nature India, and so on. Coming to the last slide, which is on World Quantum Day. Again, I'm very happy to say that today there was a very nice article in Economic Times, which I'm sure some of you have read, which talks about how India, aspires to lead the world in quantum science and technology and wishes people happy World Quantum Day from India. And I have, this is the part where yours truly has been quoted, because I actually happen to be the Indian representative on the World Quantum Day Global Network. And so this is a very special day for me. And so I'm very happy that I'm giving a talk on this day on quantum. It doesn't always happen because April 14th happens to be a national holiday in India. And so, I'm very, very pleased with all this excitement that I see in our country and the impetus that the NQM has given us. And of course, I look forward to contributing to all these efforts in whatever ways deemed fit. And of course, I have highlighted what we are going to do in quantum communications under NQM. We will be working on fiber as well as free space communication using satellite, connecting up different parts of the country in long distance forum. Then we are going to, work on fiber-based network, and then also, multi-node quantum repeater network entanglement distribution. And so this is how we are going to poise ourselves in the 8-year frame. And then going forward, we are going to connect with different countries. I have a lot of, as you know, I have, positions and affiliations in different parts of the world, and I look forward to using this platform ensuring that we actually are also globally connected, literally and otherwise. So with that, I would like to wish you a very happy World Quantum Day 2024. So thank you very much, and I can see that I stopped asking after a point whether I am still online because I saw people coming into the talk. So I assumed that I was audible. Dr. Verma, I hope that was true.
Yes.
Yes,
Definitely
okay.
lots of congratulations for your so endeavorment charge and work.
Thank you very much.
So
Yeah.
really, I am short of words that how I can compliment you for your so successful work and all that.
So that is very kind of you. Of course, all I need from you is your, good wishes and blessings, depending on how old people are, so that we can continue in whatever way we can, now with the renewed excitement that we have with National Quantum Mission. So I'll
Very
stop
good.
sharing the slide because, then I can at least see one or two people. Yeah. Sorry.
Thank you, Professor Sinha. Remarkable. Really, I will endorse Dr. Verma that we are spellbound. And
Thank you
I
very
will
much.
join Grover sir in the huge round of applause. Of
Thank you.
course, we
Thank you very
cannot
much.
unmute everyone and it will be big chaos then. But see, the participants are more than 100. 100 are only on
See
Zoom
that.
and rest are watching you on have joined your talk online on YouTube, and I can see lots of hands you can see on the screen. They are really giving you a big round of applause.
Thank
And
you.
of course, our good wishes are with you. We are sure about it that one day or today or tomorrow or the years to come, we will see your name in the maybe Nobel Prize project.
Oh, that's now I'm completely cured. I won't have that fifth dose of antibiotics.
Yeah, and a
That
lot of
just
good wishes
screw,
for your
that just
future.
messes me up, right? So today I'm going to take Dr. Sharma's comment and then I just skip that fifth dose. So thank you very much.
I will personally wrote an email to you because see at Kanya Mahavidyalaya we are representing KMV. It's a heritage institution, and our principal ma'am has a lot of dream that our girls should be given the best possible opportunities.
Right.
So maybe a visit to your lab for our masters
Okay.
as well as some of the undergrad topper students will be
Yeah.
excellent.
Yeah, we do that a lot. And actually, one of the days in which this would make even more sense would be 28th of February, because we have this, because
Yes.
RRI does a very big National Science Day, thanks
But
to our
we
founder.
don't want our girls to be part of the crowd where honestly
No, they could come around that, maybe spend a day.
Yeah, maybe we can discuss something about some projects or so later on.
Sure.
But since as I'm a moderator on the behalf of 100 participants who have dropped a lot of questions in the chat box,
I can see
I
that.
won't take much of time allocated to me. So I will just quickly go to the one or few questions in the chat box. First of all, Grover sir, people are saying lots of thanks for your encouragement and they're seeking your blessings and they want your support. You can see in the chat box. And now moving to the quantum physics questions. First is a question: how far quantum evolution would affect preliminary beings such as a human on celestial scale rather than just on quantum scale? But I think your presentation has already answered it. But even if you want to add something, please do so.
So how will it affect us as a human being on a celestial scale rather than just on a quantum scale? Of course, I mean, you know, the whole idea of, you know, the fact that we are able to actually dream of, you know, exploring different parts of the universe, for instance, you know, the whole, there is this whole field of quantum cosmology that we're talking about. So I'll just take one example, which probably is going to make this a bit more focused. Otherwise, this answer could get philosophical also. So I will just say that, you know, LIGO, for instance, you know, the gravitational wave observatory LIGO, that actually is using squeeze states to increase the precision of its measurements. So in the second round of LIGO, they are using squeeze states. These are quintessential quantum optics states. So even for a experiment of that kind, which is meant to, you know, observe and you know, sort of record gravitational wave events, we are using quantum resources to make it more precise. So this is an example of, you know, collaboration between quantum technology and a very different field, which originally, of course, did not start off by using this. In the second round, they are doing that. So, you know, the whole idea is that, you know, and then, of course, you talk about quantum communication. I am, of course, looking up all the time because I'm trying to do satellite-based QKD. So I look up a little bit more than others do. But then having said that, you know, the whole idea is that I'm planning to cover, let's say, a global scale link. So we link up the entire world, right, by using quantum links. And so that will only be possible when we have multiple satellites. And so there, it's quantum seems like a very, you know, the word quantum, unfortunately, makes it seem like it's, you know, of course, it's only quantum in its, the fact that we are dealing with, you know, subatomic physics, right? Like we're dealing with things which are at a very small level, but everything else about it is rather large in its impact. So, yeah, so just thought of giving a couple of examples. I don't know if Professor Grover wants to add anything to this question. I don't know whether the question was for him or me, given it was probably the first question after you finished your beautiful introduction.
I must say that there I can see 30 unread messages. So there are 30
great.
questions. Yeah, you can see in the chat box.
Yeah.
So we can quickly go. I think, Dr. Verma, we can take 4 or 5 questions for the time permits, or how to go about the questions. So
I think we must go with the questions because there's much of curiosity among the students.
okay, perfect. So good evening, ma'am.
Sinha ma'am allow, if Sinha ma'am allow.
Yeah, of course. Sinha ma'am, it also depends upon you, right?
Yeah. Of course, I'm fine. Yeah, please go.
Okay. Yeah, as
I
like
think 1 or 2 questions are more sensible than 1 or 2 others. Just
okay. So if you can read the chat box, please.
I can of course, you know, because I do see 30, and so maybe to pick up on 1 or 2 things which can be answered in a given time frame.
Yeah, you please pick it up. That
I like this question. I mean, of course, not the first. I mean, of course, I'm very pleased that people feel that they have contributed. So 2 questions for you. We hear sometimes that India is 10 years behind in quantum technology. Some say even 20. How does one understand such analysis? What is your assessment? This is a question I have a strong opinion on. So I picked it up because I think it's good that people hear this. See, this is the misconception that I'm trying to remove in every forum that I appear in, because this question comes in some way or the other, right? And so, of course, and then, of course, it is followed up. If it is, I don't know, social media, then people follow it up by saying, what is the point of doing something now? We are already behind. Negativity follows, and, you know, they tend to become human very quickly with quantum. So let us just understand that this particular thing is actually very untrue. So if you think about, you know, so we are the 6th country on pen and paper to have started with a national quantum strategy, right? And so in some sense, there are 5 who are ahead of us who have had national, and now there are many more. And so this is becoming quite popular. So having said that, as I mentioned, when I was trying to get funding for my satellite QKD project, even in 2016, it wasn't easy because, you know, the fact that these things are possible and that, you know, photons will actually go to a satellite 600 kilometers away. Many things had to be, you know, convinced in different ways. And then, of course, we landed up, and the Chinese satellite definitely helped us because it made it a little more real. that this thing was possible. So we have been working on theoretical quantum for a long, long time. In fact, I keep seeing Professor Deepankar Home coming in and out of this discussion, and he's one of the senior most people who has been working in theory, quantum theory, much before many other global experts, right? And so, but then the experimental part requires resources, and so we have only been able to get concerted resources for quantum with Quantum Enabled Science and Technology Program of DST, which started in 2017. So we are doing this in a focused way only for the last 6 or 7 years. So of course, you cannot expect that we are going to already produce 1,000-qubit quantum computer tomorrow if it took IBM few decades to do that. So because it doesn't happen. Why do you think it took so long to reach these milestones even globally? Because these are difficult, require a lot of resources, require focused funding. And so now with NQM, we have hope that we will be able to get this funding in the right area so that we can actually get many of these other markers that we would be only able to get with this impetus. Otherwise, we won't. And so having said that, there are many things which we have done which still are better than some other countries. So we are not just playing a catch-up game. And some of us have taken it as our life's responsibility to ensure that we do some work which is niche, which does not really follow any trend, so that later on, if it works, then it can become something which others can follow. And we also do a lot of things where we are, building capacity to reach a certain level and then beyond. So we have to understand that this number 10, 20 and all makes sense with respect to when we started with resources available for such experiments in India. And it's good that we have started now. So let's talk after the mission. Is one answer to that. And then it's a matter of great pride when multinational agencies fund research in India. I would imagine that the funding agencies will have access to the technology developed in India in which these grants are used. I wish to ask if this can compromise India's cybersecurity, which will be impacted by research. Yeah, this is a very nice question. And in fact, this keeps coming up. So we have to say that, the kind of work that people like us and my colleagues would do, we would always work on, proof of principle experiments, which will demonstrate certain R&D. And then what we are going to do is we are going to transfer this R&D to, our, I have a collaboration with Indian Navy, for instance, for maritime security. So what I am going to do is, prove that certain things will work, and then they can take it forward for the security aspect. And there is again a misconception here. Suppose you, Dr. Sharma, you are going to use BB84 protocol in your lab. And if I use BB84 protocol in my lab, both of us will, even if I know you're using BB84, I will not be able to hack into your system. So the quantum security is such that just by knowing what you're doing, I won't be able to hack. As soon as I hack, I will be letting myself be known. So it's again a wrong thing to say that just because we are developing something, we are compromising something. No. Once you take it into your bigger system and start using it, it is unhackable. So just a knowledge of the protocol or knowledge of how to do things doesn't make you a successful hacker. And that is the beauty of quantum security. So just, I thought this was a nice intersection point of photons somebody wants to know. Yeah, this one, of course, is a very interesting point. So, these photons, they come out as a pair. And so, as I said, they come out as a cone, actually. And so if you actually have a cross section, those are circles, because a cross section of a cone is a circle. But then in certain kinds, and of course it requires certain crystals, certain nonlinearity, certain alignment, this intersection point will come about when you have photons coming from both sources which are not occupying distinguishable points on the cone, but obviously points which both cones share. And that is very interesting, because if one of the photons is H, the other can be V, horizontal, vertical. But if the first one is V, then the other one is H, but you don't know which is which just by looking at that point, because you can't distinguish spatially. So as soon as you kill the distinguishability, you bring in entanglement. And that is a very interesting, and that is how we generate one kind of entangled photons in the lab. Okay. And so how can BSc students reach RRI and make our career as a nuclear or quantum physicist scientist? And a nuclear physicist and quantum physicist are slightly different from each other. So if you want to become a nuclear physicist, maybe you should go to Shah Institute of Nuclear Physics or something like that, because they're dedicated places. BSc, yes, we do have, we do take summer students. Every year we have every day I have a lot of requests, and I'm that is, I'm not very proud of my answer rate there, but then I do try my best to be as responsive as possible. And we do take, 2 or 3 who stand out as at least people who have heard a little bit more than just curiosity, because, we are an R&D lab. We're not very big. So we don't have we don't have a very big way in which we can just do something for educational purpose. We do reading projects sometimes. Okay, but then if you really have developed some understanding and have done something, then we can do something which will help you understand a few things we do. But what we do is not that easy, and so it becomes a challenge. But we do have students every year who do this, right? And so these are all, of course, very nice, flattering things about Indian quantum and our work. So I'll start. How data are transferred through light fidelity system. I don't know what, I mean, I don't work on Li-Fi, so I will skip that question. Internship, I think we just discussed the internship one, I think. Same question, amazing work. I'm just going through this.
Yeah.
Yeah, and so most of it
And
is the first.
I can also ask
Yes,
if
please.
you like, I can take the liberty to.
Of course, yeah, please.
Okay.
Yeah, yeah.
So what I observe, because I'm a material scientist, right?
Hmm.
So I observe that why quantum physicists, they are confined, because I don't see much of overlapping in a kind of different merging with different streams, coming up with a combined models or something. Like in my field, I work in glasses. I have never seen work done to understand the properties of glasses, some quantum modeling or done on their.
That's a very good question and very interesting one, because I just day before yesterday I was at lunch with a colleague who works on rheology, and she works on glassy systems, then also clay. She's a professor at RRI. She has a lab, soft condensed matter, and so she was actually saying that she would be interested in sort of figuring out some of the underlying principles, because there is some synergy between how these systems work and how, for instance, certain things happen in cold atoms.
True.
And so we also have a lot of very interesting cold atoms work going on at RRI. And so, at some level, there is a commonality between the, because ultimately there is a, commonality in the how you can explain it through statistical physics. And so some, maybe there is some kind of a Brownian motion, which is common between a cold atom system and a glassy. And so there is some already, even at RRI, and as of day before yesterday, I heard that there is, some discussion happening between the cold people and our colleague from SCM. So this is happening, but then it is more happening. Let's say, for instance, you belong to, so quantum materials is an area, of course, which is a very interesting one. And so, of course, there is materials for quantum and there's quantum for materials. Now, quantum for materials is much older than the current excitement, because to be able to explain various things which are happening in material science or condensed matter through quantum happens, right? It has been happening for a while. But then, of course, materials for quantum is very exciting. So, I'm working with single photon sources, I'm working with detectors. If you can come up with a material which will give me more than the kind of quantum efficiency that what I see from my commercially available, already it becomes useful for the quantum mission. Okay. And so, so there is a lot of things which
but
just
I think
require
these
a little
kind of
imagination.
platforms, they give an insight. Like, for example, for not even for 1 second, you're a very good presenter, I must say that. So not even for 1 second, like, I lost your slide or get connected, and the way you flip on between different slides. So I think we need more this kind of platforms where we can interact openly, exchange ideas, and we can really, break the boundaries.
Sure, I'll be very happy to contribute.
Thank you so much. And now we can move on to the next
I think
session.
Professor Ahluwalia has raised his hand.
Yes, okay.
Yeah. So thank you very much, Professor Urbasi, especially for being on the World Quantum Day with us. IAPT is proud of your achievements, and I send on behalf of IAPT community our good wishes for your future programs also.
Thank you very much.
And I have a few questions, in my mind from IAPT point of view also, because we are a community of about 10,000 teachers around.
Right.
We are actually hearing a lot about the need for developing workforce for quantum technologies and quantum mission.
Mm-hmm.
Now, it's sounds very nice. I mean, but sometimes, we feel that we do not really know in a way that how we can go about it, say from schools to colleges to the universities, and bringing those kinds of courses into the physics curriculum, which can really help us create that kind of a workforce very rapidly. And we become part of a big mission of the country itself. Because sometimes we are told that there are lots of opportunities of employment which are also going to be there.
Right.
I think when we go into, say, a physics department, sometimes people ask us after doing our MSc physics, where are we going in terms of employment opportunities? Maybe technologists have lots of possibilities, but when physics people go into basic sciences, for example, they look for and they really look forward to these kinds of questions that, look, where are we going? Are these kinds of excitements going to get us some opportunities? And how can we prepare ourselves for that? That is the question which has been coming to my mind, and I thought I should really look for a kind of an answer from you that how can we prepare? By the way, let me also tell you one thing which IEPT is going to do from 22nd of April, this month itself. We have chalked out a program for about 2 weeks to train teachers from schools and colleges and students on quantum computing itself. It's a kind of a primer which we would like to really unfold to the teaching community from schools. So in the light of this, your opinion and your guidance can be of great help to us. Thank you.
Thank you very much, Professor Ahluwalia. And of course, what you say sounds very exciting that you're doing this from 22nd of April. So the National Quantum Mission actually, the way it was written, because I was also in the draft project report committee. So we actually have 4 mandates. One is, of course, research and development. And, then of course we have technology development. Then we have, different kinds of collaboration, national and international. But the 4th and very important pillar is actually human resource development. And so human resource development, we have an entire chapter on that in the project report. And so the point is that, we have come up with different suggestions that have already been given in the report, which of course the Department of Science and Technology, is going to take up. But then as a part of our current, what we have just finished doing is writing these 3 proposals for various technology groups, which will ultimately lead to the formation of these hubs that we just talked about in the talk as well. And so the technology groups, while of course we have identified the specific technology and science that we will be focusing on and all that, one of the main things that is going to be evaluated as well is our preparedness, and as well as our thoughts on how we are going to contribute to the human resource development. And so we of course we have already said things like we should have, even as a technology group which is focused on, let's say, a small subtopic of the whole mission, right? It's not about just quantum computing. Let's say photonic quantum computing is a technology group. So even as a part of that, we are going to have, a regular, both student and teacher training programs. So the idea being that, there's going to be resource available, allocated for that. So the whatever the resources that we are talking about under the mission is not just for the development of the technology, but also for the development of the people who will work on this now and in future. And so and then also different, like for instance, IISc, as was mentioned, they came up with the MTech in Quantum Technology program 2-3 years back. Then more recently, IISer Pune has come up with an MSc in Quantum, technology program. So I think, all these institutes which already have undergraduate teaching, one after the other, they will follow this model and get also resourced to do that. And you just can't can't set up a program if you don't have the resources to do that, right? So this is a mandate of the national mission actually. And so of course, and of course, since we have been involved in it from the beginning, so I'm hoping that once it takes shape, this will actually see a lot of these ideas actually come through. So not only will we have dedicated workshops and conferences, and also these schools, as the SCRC school type thing for quantum, but then also we are going to have different impetus for these undergraduate teaching places, not just the IITs and ICERs, but also the universities, because that is where we have the maximum workforce, future workforce. And so this is a part of the mission. And of course, we've written it with all good faith. And now we have to hope that it actually happens that way. And I mean, I don't see why it shouldn't.
Actually, there was one request,
Yeah.
Please,
Please, I
can't use this opportunity to not make that request. And that is, please keep IAPT also in that loop when it comes to making, some decisions to do these kinds of programs.
Absolutely, absolutely. I think this is probably the largest organization of its kind. And so naturally, it is a natural organization that one should, sort of appeal to and also, sort of involve, right? Both ways.
Happy to know, ma'am, that simultaneously, there are two programs which we were running nationwide on this Quantum World Day itself. And we didn't restrict it to one day only. We had full programs which we brought on the table for people to look at it and excite them also. And the excitement, I think you can judge also that we have a Zoom platform for 100 people. And also there were lots of people on the YouTube also.
Right.
So we have
Congratulations. Yeah, I think you've done a remarkable job. And so, I mean, and of course, you've been doing this consistently for various physics related things. I've also, as I said, somehow, thanks to you, and I have been.
But I would like that you become life member of IAPT. I invite you to become a life member of IAPT. We have a website. You can just go. It is just a click away, ma'am.
I see. Thank you. I will definitely look into that. Yeah. Thank you
for the time that you have given us. And I have no words to say that how absorbing your talk was. I mean, it was
just very kind. Thank you.
Dr. Vandana Luthra has raised a hand. So before we can move on, ma'am, you can unmute yourself.
Thank you very much. First of all, a mind-blowing talk, and the kind of knowledge you have provided is also telling us that what all is happening in India. Other than that, I just was seeing the 4 verticals of the National Quantum Mission. In that, if there was a space for the outreach program in a different manner, like there can be a short term and a long term, because when a student or a teacher goes for a training, and if that training is for just say 15 days, that may be just not sufficient in order to have the contribution in that particular field. So if the teachers in the undergraduate college, because partly you have answered my question, but I would like to suggest that if there can be a long-term trainings in which when they learn and they are able to contribute also, especially quantum materials. I think condensed matter physics is something which is being pursued in India with great success. And in that, many people are working in low temperature field also. And low temperature, and when we are talking about cold atoms, in that case, I think that their knowledge can also be utilized for these kind of applications. So in that case, I would say in the outreach and in the capacity building, if the teachers can also take part in long-term trainings and their contributions, I think that will be something which may be also useful. Thank you so much.
Thank you for the suggestion. I mean, and of course, at the right moment and opportunity, I'll definitely place all these points, when we actually go on to the next step. And as I mentioned, definitely this is an organization which should be involved in different capacities. So thank you for your,
Thank you very much.
Professor Sinha. Thanks a lot. As you are representing India at globally as well as many national platforms. So as the Professor Ahluwalia has rightly said that we need more representation, through IAPT and through other programs. We need more quantum involvement. In these kind of programs, they brought all the researchers, students, professors to one platform. So it's really, really informative. And finally, Alice has reached the wonderland or the quantum land. We can see that Alice has completed her travel journey very successfully and nicely. And
but are you sure? Given that this is quantum, can you really be sure?
Quantum.
there's always a probability of not.
True.
So I just wanted to say that, I have a meeting with a Canadian colleague starting in 15 minutes. I have a personal thing to attend to in that 15-minute time. So if it is okay, then if I can
Yes,
take your
sure,
leave
please.
for now. Yeah,
Yeah,
because I
yeah,
can see that
yeah.
I'm going
Okay.
to pushing it a
So
bit fine. So thank you very much for your time and, for the opportunity. It
thanks,
was, as always, wonderful interacting. And so I'll be in touch, Professor Ahluwalia.
thank you.
For
Thank you
various
so
things.
much.
Thank you. Thank you.
Thank you. Thanks a lot.
Thank
Uh,
you. Thanks
before
a lot, Professor
Yeah.
Sinha, for your so insightful talk. Really, to make us all aware about quantum mission and future of quantum world. I wish our IIPT members and personally I wish PG students of my institute, Kanya Mahavidyalaya Jalandhar, may get the chance to visit at RRI either through internship or any other program as you suggest. So I kindly request you to be connected with us for our future endeavors, please. Hope to meet you soon, ma'am. Really, words are not enough. Once again, I am saying words are not enough to say thanks to you.
And we can move on to the next part of the session, that is a report by the coordinator, Dr. Neetu Chopra Verma. But before I invite Dr. Verma, as a colleague, I have witnessed that she has worked a lot to make this successful happen. Many phone calls, emails, messages, and it is a 24/7 job or the efforts she has done. So we can give a big round of applause to her. Of course, we can raise our hand and we can clap for her because she has done a lot. Being an IIPT member, a very nice researcher, innovator. I invite Dr. Verma to read the report for all these 6 days. Thank you. Over to you, Dr. Verma.
Thanks, Dr. Gopi, for inviting me for the report of 1 week national workshop. Before start of my report, I would convey my sincere thanks to all of you for making this event a wonderful event. A very good evening to our chief guest, Professor Arun Grover, former Vice Chancellor, Punjab University, Chandigarh, Professor Urbasi Sinha, Head Quantum Information and Computing Laboratory at Raman Research Institute, Bangalore, Professor P.K. Ahluwalia, President, IIPT, Shiksha Ratan Jaswinder Singh, President, IIPT, Regional Council 2, our worthy Principal Ma'am, Professor Dr. Atima Sharma Dwivedi, all dear colleagues and participants of Alice in Quantum Land. On behalf of organizing committee, I deem it a great honor and privilege to present report of 1 week online workshop on quantum physics, that is Alice in Quantum Land. 6 days workshop held from April 9 to April 14 offered a platform for 984 physics aspirants to explore the complexities of quantum mechanics through keynote presentations, panel discussions, quizzes, and hands-on workshop. Participants were immersed in a world of discovery, guided by leading scientists and practitioners in the field. April 9th, 2024, the inaugural day of Alice in Quantum Land workshop marked the beginning of an enlightening journey into the world of quantum mechanics. On this day, we have conducted on-campus program in morning from 10 a.m. to 2 p.m. along with the online program from 6 p.m. to 8 p.m. evening. During on-campus program, Professor P.K. Ahluwalia, President of IIPT, and Professor K.N. Joshipura from Sardar Patel University, Gujarat, addressed the participants the basics of quantum mechanics in the campus of Kanya Mahavidyalaya Jalandhar. The evening online session, inaugurated by Professor Atima Sharma Dwivedi, Principal Kanya Mahavidyalaya Jalandhar, saw approximately 500 participants from across India engaged in intellectual discourse and discovery. Professor Arvind, Vice Chancellor of Punjabi University, Patiala, and Professor at IISER Mohali, set the tone with a keynote presentation titled From Quantum Mechanics to Quantum Technologies, a Journey of 100 Years. The session concluded with the release of an open book online quiz by Dr. Uttara, Head DDJD Vaishnav College, Chennai. Again on second day, that is 10th April, we have conducted on campus as well as online program. During on-campus program includes hands-on workshop, witness a participation of 400 students from other institutes at Kanya Mahavidyalaya Jalandhar, and the session was conducted by Shiksha Ratan Awardee Professor Jaswinder Singh, and it was an amazing experience for students and faculty. The online session of the workshop had an expert talk by Professor Ajoy Ghatak, Emeritus Professor at IIT Delhi, and Meghnad Saha, Distinguished Professor by NASI, who delved us into the world of two-hole interference experiment. Participants gained valuable insights into the quantum phenomena related to interference and wave particle duality, further deepening their understandings of quantum mechanics. Day 3 commenced with a panel discussion on unveiling quantum mysteries, having Professor P.K. Ahluwalia, President IAPT, Professor Raman Johal from IISER Mohali, Professor Manjeet Kaur from Punjab University, Chandigarh, and Professor V. Madhurima from Central University of Tamil Nadu. The discussion centered on bridging the gap between scientific understanding and everyday life, providing participants with valuable perspectives on the practical implication of quantum mechanics. The highlight of the fourth day was an expert talk by Professor P. Deshmukh, RV Chair Professor at RV University, Bengaluru, titled Complexities of Quantum Land. Professor Deshmukh provided a comprehensive overview of quantum mechanics, addressing fundamental concepts such as uncertainty, superpositions, and many more. Participants gained insights into the historical evolution of quantum mechanics and its practical applications, enriching their knowledge and understanding of subject. Day 5 had an expert talk by Professor Vanna Luthra from Gargi College, University of Delhi on contemplating quantum mechanics, followed by a movie screening and quiz. Professor Luthra's sessions enlightened us about the invaluable contribution of Indian scientists through the captivating video presentation. The day concluded with the participants' active participation in quiz, consolidating their understanding of quantum mechanics. The final day of the workshop showcased an expert talk by Professor Urbasi Sinha, Head of Quantum Information and Computing Laboratory at Raman Research Institute, Bengaluru, on the magical world of photons. Professor Sinha's presentations offered valuable insights into quantum information and computing, inspiring participants with the potential applications of quantum technologies. The day concluded with a sense of fulfillment and enthusiasm as participants reflected on their journey through captivating world of quantum mechanics. With this, the Alice in the Quantum Land workshop provided a platform for the participants to explore the wonders of quantum mechanics through expert talks, panel discussions, quizzes, and hands-on workshops. Each day offered unique insights and experiences, enriching participants' understanding of quantum phenomena and their applications. With the success of 6-day-long online workshop, I wish to propose vote of thanks to all of you. First and foremost, I wish to express my heartiest thanks and gratitude to our worthy chief guest of the valedictory session, Professor Arun Grover Ji, for his gracious presence. Thanks a lot, sir, for sharing insightful and thought-provoking remarks. I am thankful from the core of my heart to Professor P.K. Ahluwalia, President IAPT, and Professor Jaswinder Singh, President IAPT Regional Council 2, for providing all the support and guidance to make this event a remarkable one. I also express my sincere thanks to our pillar of strength and our dynamic principal, Dr. Atima Sharma Dwivedi, for her consistent guidance, support, and motivation during the organization of this event, without which it would not have been possible to make it elegant. We are extremely indebted to all eminent speakers, Professor Arvind, Professor Ghatak, Professor Deshmukh Ji, Professor Urbasi Sinha, Professor Vanna, Professor Manjeet, Professor Johal, Professor V. Madhurima, and many more who have updated us a lot with their effective and intellectual talks. I pay my gratitude to all mentors of the workshop, Professor Rekha, Secretary IAPT, Professor Sarmishta Sahu, Professor Arvind Kulkarni, Professor Minakshi Syal, Professor Vanna, and Dr. Utra, for their valuable guidance. Thank you so much for being a part of this 1 week event. I also acknowledge the constant round-the-clock efforts of members of organizing committee, faculty of PG Department of Physics, Kanya Mahavidyalaya Jalandhar, who have worked hard to make this event a possible one. I appreciate the sincere efforts of our PhD scholars of PG Department of Physics, KMV Jalandhar. My sincere thanks to technical support by Mr. Shashi from KMV Computer Science Department for their complete assistance. I also thank all the participants for their healthy interaction and participation in the workshop. I am sure that our participants have learned a lot from the expertise of the resource persons. Once again, I express my deep gratitude to all of you for being a part of this historic landmark event and making it so memorable and special. Once again, thanks to all. Thank you. Now I would like to share the glimpses of this 1 week program through a small video. So Dr. Sandeep, please share the video. Dr. Sandeep. Music is not there. Check the audio quality, please.
Ma'am, I have played the video. Is it not audible?
It's not audible. No issues. Still then, it's fine.
You have to click on share sound.
If possible, you can click.
Thank you, Dr. Haleen.
Okay, ma'am.
Okay, and before we move on to the next for our presidential remarks by Professor Jaswinder and by guest of honor Professor Rekha, we will just have two feedbacks from the participants. One is Sistela Hemant. I'm sorry if I'm pronouncing your name in the wrong way. So can you please unmute yourself and restrict your remarks to 2 minutes, please? If I'm audible to Sistela Hemant.
Sistela Hemant is from Andhra Pradesh.
Andhra, okay.
Yes.
Mr. Hemant, are you there? If not, then we can move on to Tapas Kumar Naik.
We have made him as a co-host.
Okay. So
is he there? Dr. Gopi, let's pronounce some other name.
Yeah, Tapas Kumar Naik. If you're here, please, you can share your remarks. If there is any technical issue, please drop a message in the chat box. Our technical team will look into it. I couldn't see any.
Good evening, ma'am.
Yes.
Okay. Yeah. Okay. So please switch on your video so that we can see who's speaking.
Okay, ma'am. Okay, ma'am.
Okay. Yeah. So we have Tapas Naik. Okay. Over to you.
Okay, ma'am. Thanks, ma'am, for the opportunity. Good evening, esteemed participants and distinguished experts in the field of physics. My name is Tapas Kumar Naik and I hail from the beautiful state of Odisha. Currently I am in the final year of my BSc Physics program at Fakimohan University. Since childhood, I have been captivated by the enigmatic darkness of the night sky, finding solace and inspiration in its vastness. This fascination with the mysteries of the universe led me to pursue a deeper understanding of physics, particularly in the realm of quantum mechanics. My journey into the world of quantum physics began in my 4th semester, and ever since then, I have been on an exhilarating quest to unravel its complexities. As Albert Einstein famously said, imagination is more important than knowledge. And indeed, quantum physics encourages us to push the boundaries of our imagination and delve into the realm of the unknown. It is with great pleasure and excitement that I participate in this week-long nationwide workshop titled Alice in Quantum Land. Each day of this workshop has been a journey of discovery and enlightenment for me, from insightful talks by esteemed professors to engaging quizzes and discussions. Every moment has been filled with learning opportunities. One particular highlight of the workshop was the enlightening talk delivered by Professor Ajay Ghatar. His clarity in explanation and ability to simplify complex concepts resonated deeply within me, making the intricacies of quantum physics more accessible and comprehensible. Moreover, the real-life examples shared by the experts have enriched my understanding and ignited my curiosity further. As the workshop draws to a close, I feel a sense of gratitude for the invaluable knowledge and experiences gained. The newfound confidence and insights acquired during this workshop have instilled in me a deeper passion for physics and a desire to continue exploring the wonders of the quantum land. In conclusion, I express my heartfelt thanks to the organizers, professors, and fellow participants for making this workshop a memorable and enriching experience. I eagerly looking forward to participate in such kind of events in near future. Thanks, ma'am. Thanks for the
Thank you, Tapas. Thank you so much. It's very nice to see such young blood, very enthusiastic and committed toward the work. Of course, India lies on the shoulders like you. So on the behalf of all these participants, I will take this feedback and we can move on to special remarks by our own Professor Rekha Ghorpade. Over to you, ma'am.
Thank you, Madam Sharma.
Ma'am, please unmute yourself.
Unmute yourself.
Thank you, Professor Upi. Respected chief guest for the today's function, Dr. Arun Grover, President Professor P.K. Ahluwalia, Professor Jaswinder Singh, President IPT RC02, Principal Madam Atima Sharma, the entire organizing committee, and my great friend Professor Neetu Verma, and also the wonderful participants. Let me give you the greetings for the World Quantum Day for today. And I'm really happy to be a part of this function for the, and I feel very proud to be the part of the function. I must congratulate Dr. Neetu Verma for taking the initiative to celebrate this World Quantum Day in such a great way by organizing a week-long program that is Alice in Quantum Land, that is a national workshop. And I'm really happy to note that there were about 900 plus participants registered from across the country. And I think this is a great achievement of this program also. First of all, let me regret for the party. I mean, our Zoom platform could not accommodate so many participants. We have a limitation of 100, but the entire event and all the sessions were live streamed on YouTube. So that was the wonderful thing. For this reason, I must thank not only, the entire technical team along with Dr. Neetu Verma from Kanya Mahavidyalaya. I think because of them, the whole YouTube streaming was possible, and the entire program went on very well. I wish to place on record the sincere gratitude towards all the speakers, Professor Arvind, Professor Ajay Ghatak, Professor P.C. Deshmukh, Professor Vandana Luthra, Professor Urbasi Sinha, and all our panelists on the panel discussion. That is our own president, Professor Ahluwalia, Professor Manjit Kaur, Professor V. Madhurima, and Professor Ramdeep Johal. I think this whole workshop, national workshop, was a great success. I heard from many participants that this kind of workshops should be held very frequently, and the entire fear of quantum mechanics has really washed off, and people have started, liking the subject in a way this particular workshop was conducted. This the entire transformation from quantum mechanics to quantum technologies and quantum computing was covered in a very lucid way. And that is the success of this particular program. Today's session was a cherry on the cake. I think Professor Urbasi Sinha, I must congratulate and also feel very proud that we have a great contribution through her to the program, like QuIC along with ISRO and QuIC with RRI, and especially the QKD networks. Her contribution was incredible. And she has also highlighted some positivity where generally we normally lack in that we feel that Indians are lacking in all fronts of technologies and other scientific endeavors. But I think she has really shown a very, very good way, or maybe she has washed off this negativity and shown us a positive path that India has a great contribution in all the fields of research. She has also underlined, I think, the great potential in the field of research of quantum information and computing. And I think this is a great thing that for the students who are the participants in this program, we must have noted this whole thing. I think I should not take much of a time. It is more than 2 hours, but I'm really overwhelmed by this particular national workshop, the way it has been conducted very methodically, and the great contribution from Kanya Mahavidyalaya, the entire organizing committee at KMV, the mentors. I think Professor A.G. Kulkarni must be here. He has, I think, triggered this idea of having such kind of workshops. Professor Sharmishta Shahu, Professor Minakshi Sayal, Professor Vandana Luthra, and Professor Uttara. If I've forgotten any names, please pardon me. But the entire event was really a very great success. I think this is a beginning for IAPT, and as a teacher ambassador, Dr. Neetu Verma has done a great job, a great round of applause to her. I sincerely thank you and congratulate you for conducting such a great event. Thank you very much. Thank you, everyone. Thank you, all the participants.
Thank you, Professor Rekha. Thanks a lot for very kind words. So, on the behalf of Kanya Mahavidyalaya, as well as Dr. Verma and the principal ma'am, I would like to ensure that KMV will always contribute to whatever the cause of physics or science, technology, quantum, nanomaterials, and so on. We are always, as a team, we are present 24/7.
Thank you
So
so much.
before we
Thank
end
you.
this evening, and I would like to have, I would like to invite our own, it seems our own, because meeting sir in the auditorium, looking at his way of work and interacting with the students, not only the student, even like I feel like sitting on the sofa and attending his workshop on and on and on. So I can say our own Professor Jaswinder sir for your presidential remarks for the overall. Please, over to you, sir.
Thank you, Ji. Thanks to the whole IAPT National Committee members, either President Aluwalia, Secretary Ma'am Rekha Ji, thanks to this Principal Ma'am Atima Ji, Dr. Neetu Ji, and all the other associate members. This was a really a successful workshop, I can say. You have committed to the work. You can convey each and everything. Weak men wait for opportunities, but strong men create them. And Neetu Verma has proved it. So it's a great day for us, that quantum day we have celebrated in 2024. I'm thankful to the whole community of physicists. And I would like to say that if we really want to convey our message to our young kids, those are at quantum level, you can say, then we can explore more and more ways to this quantum land. Thanks to all.
Thank you so much, sir. Thanks a lot. Before we close this event and say goodbye, unfortunately, we cannot deliver dinner on the through any kind of quantum, so we cannot serve. We cannot have a dinner together. But on our dinner tables, we are definitely going to discuss about this, about the 7 days workshop. But before we end it, I will just like to request President Sir to give the overall remarks or the concluding remarks and give your blessings and thanks to the wonderful participant and the audience. Over to you, Aluwalia sir.
Dr. Gopi, I think it has been a joy for me, to put it very simply. I think before I forget, I must also thank all the ladies of the college who have done so much hard work, and also men supporting them. That was great. I mean, that is what I learned from Kanya Mahavidyalaya, that you are a team, and whenever teams work, they always succeed. We should never forget that. IEPT is also a team at national level, and all our RCs are a very important part of that. You are very lucky that you have President Jaswinder Singh Ji, who is himself a person who believes in doing and not just dictating. So that is also great about this program. I think when we thought of this program, a wonderful thing happened, which was this, that a team got into place. Let me tell you that Professor Kulkarni is a wonderful man who always really pushes for better and better things. And he expects us. He's an elder of IAPT, and I really enjoy talking to him. Sometimes we spend an hour also discussing about various opportunities which can be created. And another thing which is a kind of an offshoot of this kind of a work culture in IAPT, that we are going to see another program emerging very soon from 22nd of April. All the participants who are here in this particular program, I'll request them that you can still register for that and be a part of it. We are actually interested at the IAPT level that we should really flood our young minds with the opportunities which are waiting for them in this quantum mission itself. And I think that is possible. I must thank all the experts. They are very dear to us. Without any kind of a problem, they all said yes to our request. Starting from very senior Professor A.K. Ghatak ji, Professor P.C. Deshmukh ji, Professor Arvind, Professor Vandana, and all those people who have been part of this program. It has been a joy to hear. Today, we heard about something which is the future of this country. And that future is being brought by, I would now always call her Quantum Lady of India. She did a great job in really delivering the final, what you call, message to each of the participants here, that what is in store for them in future via physics. Please don't forget that. This is always via physics. And I think this is very, very enlightening moment for each of us. I would also like to mention here in this workshop that there was a parallel workshop which was going on in RC Bihar. I listened to 2 lectures there also before this workshop itself. My day used to be, very, very heavy as a result of that. And today there was one lecture there by Professor Shraddha Singh from USA. Very nice lecture, I would say. There was another lecture by Professor Panigrahi, who has been former director of ISER Kolkata. And I think we have now a team of people on whom we can bank upon. And we have a team sitting at Jalandhar, whom we can always tell, please come on and do something for IAPT. And I know that you are going to do a great job in future also.
Sure, sir. On the behalf of Principal Ma'am and the whole management, I can commit for that.
I was just going to say one thing. I met your Principal Ma'am also.
Yes,
I
sir.
think all positive vibes emanate from her.
Yes,
And
sir.
she is such a supporting person. And congratulations, Kanya Mahavidyalaya.
Thank
for
you,
your
sir.
Thank you.
And this means that you can create very many things which will be kind of pilots for the whole country. So
Thank you, sir.
congratulations once again. Thank you,
Sure.
IAPT. Thank you, participants. Thank you, Ma'am Rekha. See, everywhere women are there. She is one who takes all of the burden from me. Look at Ma'am Meenakshi Sayal. She is the person behind Lucy. Let us solve it. I have no words to express. I think I am very lucky that we are having such a fine set of people. And Professor Jaswinder Singh is my friend. I want to travel with him in his car. I hope he will give me an opportunity. So thank you very much
Thank you, sir.
all for this great workshop.
Thank you, sir. Thank you. With this, we end this our journey of Alice in Quantum Land. Wish you all a very happy good night and many more successful endeavors for years and years to come. With this, I, Gopi Sharma, wish you bid you farewell to all of you. Jai Hind. Take care.
Thank you. Thank you, madam.
Thank you. Thank you, everyone, for making it a
Thank
success.
you.
Thank you. And very special thanks to Professor P.K. Ahluwalia ji,
Yes.
because at every inch of the walk, he was with us. Whenever we have a problem, then he was just on one click of the call at any time. So thanks a lot, sir, for your so great efforts with us. Thank you, sir.
Thank you.
Thank you. Thanks to all. Thank you.